So natural log 4, natural log 1 is 0. This is divided by 3. And the left-hand side is natural log prime, which is 1 over x or 1 over c. What type of equation is this, and how do I get c from here? What would you do to get c? How do we get c here?
Cross multiply.
Very good. Here is a tiny, tiny trick. If this is 1, just flip them both at the same time. Only if this is 1 and your variable is here. So c equals 3 divided by natural log 4. I don't believe this. I have to check. It has to be between 1 and 4. If it's not between 1 and 4, then something is wrong. So just checking natural log 4. And I got 2.16, perfect. So this is the number that is guaranteed by the mean value theorem for the given function on the given interval. Okay, I'd like to look at an application of this. Any questions on the mean value theorem so far? Okay, page 5. Okay. We are given, suppose, that we have 3 less than or equal to f prime of x, less than or equal to 5, that they say, for all values of x, for all x. So this relationship happens for this function, f of x. Its derivative is somewhere between 3 and 5 for every x value. Fine. It says now, show that 18 is less than or equal to f of 8 minus f of 2, and that is less than or equal to 30. So this is what we are asked to show. Okay, so the moment I'm told that the derivative of this function is between 3 and 5, I'm automatically, I know for sure that, so from this relationship, I know that f of x is continuous for all x, and its derivative exists for all x. So f prime of x exists, or I can say better, f of x differentiable for all x. So these are the hypotheses of the mean value theorem. You can say even Rolle's theorem, correct. But the fact that I'm looking at f of 8 and f of 2, that makes me believe that they want us, or they're triggering the mean value theorem, not Rolle's theorem, because of the difference. Okay, now I'm really looking at, obviously, the interval 2, 8. So the function is continuous for all, is differentiable for all, including, of course, 2, 8. So because the two conditions or hypotheses of the mean value theorem are fulfilled, I can say that by MVT, there must exist a C in this interval, in the interval 2, 8, such that f prime of C equals f of 8 minus f of 2 divided by 8 minus 2. I don't have the function. I don't know what f of 8 is. I don't know what f of 2 is, because I don't have the function. Unknown. But I am told that the derivative evaluated for anything I want must be between 3 and 5. So I have a derivative here. So this must be f prime of c of anything for any real number must be between 3 and 5. But by MVT, f prime of c equals this. So I'm going to replace f prime of c by what it equals to. So therefore I have 3 less than or equal to f of 8 minus f of 2, of course divided by 6, which must be less than or equal to 5. So let's peek, and that's not cheating. This is what they want us to show. And now let's see where we arrived at, and what do you think we should do? Very good. Multiply all 3 sides by 6. And let's see what we get. So that's my 6. So 18 less than or equal to f of 8 minus f of 2 less than or equal to 30. Any questions? And this was a application of the mean value theorem. Any questions, please? Any questions? Okay, so I would like to continue then with 4.3. And 4.3, we already have the groundwork done for 4.3. 4.3 deals with the first derivative and the second derivative and what they say about the function. We already talked about the first derivative test. First derivative test. What is the first derivative test? We already discussed that when f prime of x is greater than 0, f is increasing. When f prime of x is less than 0, f is decreasing. And when f prime of c is 0 and the sequence of signs is or undefined, or f prime of c is undefined, and the sequence of signs is positive, 0, negative, or positive, undefined, negative, c gives a maximum. And, when f prime of c is 0 or f prime of c is undefined, and we have negative 0 positive or negative undefined positive, c gives a minimum. We already discussed about all that. So this is basically the increasing decreasing test. Increasing decreasing test, and this is specifically the first derivative test. We also have the second derivative. So let me summarize again what the first derivative tells us. So f prime of x gives increasing, decreasing intervals, and it also gives max min. We will also look at the second derivative. What will the second derivative give? Two different things. Concavity. So a function can open up, concave up, or it can open downwards, concave downward. So the second derivative will tell us concavity. Here, the second derivative is greater than 0. For this situation, the second derivative is less than 0. Also, the second derivative will give us inflection points. What is an inflection point? The function opens downward, and at this point, it starts opening upward. This is what is called an IP. Of course, the other way around. It can be opening upward, and then all of a sudden, it changes concavity, opening downward. This is also an IP. Inflection point. There is something called the second derivative test, but I want to go through an example step by step, or at least one, maybe two, before I talk about the second derivative test. So, if you'd like, you can choose, if you have your WebAssign ebook open at the end of 4.3, and before you find a problem, I will start with one. We're not going to do the graphing. We're going to go through everything and get it ready for graphing. Or maybe if we're ready, we can also graph. Okay, so I'm going to start with a polynomial function. If you want to choose a polynomial function and give me one, that will be great. That will be even better. If not, I will choose one. Should I wait or should I go? Sorry, I'm kidding. You know the song. So should I choose? Anyone is? Yes? Okay, I will choose then. So let's say f of x is 5x cubed minus 3x to the fifth. Okay, I don't want to touch this. I would like it out of the way, but okay, I don't know why this is in the way. Anyway, I don't like this shadow here. Anyway, so first of all, please get used to this table in which f prime is the first row. Of course, x is the first row, but what I mean is f prime, and then f of x, and then the second derivative. First, we will learn everything that we can from the function itself. So let's see what I can learn. So first of all, the domain of this function is all real numbers. It's a polynomial function. I will immediately factor out what? Anyone?
X cubed.
Thank you very much. And even negative x cubed. And then I get 3x squared and then minus 5.
You wrote x to the fifth instead of x cubed.
I did.
There we go.
Thank you very much. So we factor negative x to the third, and we have 3x squared minus 5, which is ugly, right? Because when I set this equal to 0, I will get two impossible solutions. Not impossible, you know what I mean. Okay. So, secondly, I will plug in 0, and I get 0. I will immediately determine these limits. Not difficult. Which of these two terms is the most powerful when it comes to infinities?
1 raised to the fifth.
Yes. So this doesn't matter. So when I plug in, I shouldn't say that, but when I look at the end behavior when x approaches negative infinity, what do I get here? Anyone?
Positive 30.
Very good. And what do I get here?
Negative 30.
Perfect. And now I only want the x-intercepts. I already determined this. It's 0. And remember, when we look at triple solutions like those, there must be something, a cross, but a flat cross. Okay, you may remember that or not, it's okay. So now, when I set this equal to 0, the function equal to 0, I do get x equals 0 3 times. And I get that 3x squared minus 5 is 0. I move 5, divide by 3, yada yada, plus or minus the square root of 5/3. That's what I was saying. This is an impossible situation because I will, if we decide to graph it, and why not, we can, I will have to graph. So this is 5 divided by 3 raised to power, there was the square root. I don't need that. Okay, so square root of 5 divided by 3. So I get 1.3 plus or minus 1.3. So then I have negative 1.3 and 1.3, 0 and 0. So at this point, there is nothing I can find about the function from the function itself, and I will move on to the first derivative. So I differentiate the function. Can anyone give us the derivative of this function? I would write it down. Anyone? 15.
15x squared minus, I can't see the top of the problem. There we go. Okay, up number 15. 15x to the 4th.
That's it. So I know that this will never be undefined. Critical numbers would not come from f prime being undefined, but will come from f prime being 0. So it's degree 4. I have to find 4 solutions for this equation. This, I, of course, divide by 15. So I have x squared minus x to the 4th equals 0, or x to the 4th minus x squared equals 0, and I factor out x squared. And that's how I get those 4 solutions. 2 of them are 0, and one is positive 1, and the other one is negative 1. Is that okay so far? Yes? No? Maybe?
Keep going.
Very good. Good. So then we have x equals 0 twice, and we have x equals plus or minus 1. These are critical numbers. We don't know which of these will turn eventually into a max min. We will do that right now. So 0, and of course it had to be negative 1 and 1, so that I can squeeze everything in here. Okay. At this point, I have to find the sign of f prime. So f prime one more time, and this is 15 x squared and 1 minus x squared. So when I try to find the sign of the first derivative, before I do that, I have to find this number and this number. So when we plug in negative 1, negative 5, plus 3, negative 2, and 5 minus 3, 2. So now I have to study the sign, but I will not waste my time with the sign of 15x squared. I will only talk about this. So when I plug in negative 10, well, we know what the sign is all this, right? Because it's, if you just want to imagine to graph, we're not graphing the derivative. But if you want to graph this, it crosses at negative 1 and 1. So it has to be positive between negative 1 and 1 and negative between negative infinity, negative 1, and 1 infinity. So I know the sign. So this is positive here and negative here. But you can check. So with 10, 1 minus 10, with negative 10 or positive 10 has to be negative. And in between negative 1 and 1 will be positive. Okay, at this point, I make sure that these two rows work well together. If not, I'll say oops and go back to the drawing board. So from positive infinity to 0, the function is decreasing. Is that supported by the first derivative?
Yeah.
Very good. From 0 to negative 2, the function is decreasing. Is that supported by the first derivative, the sign of the first derivative? From negative 2 to 0, the function is increasing in values. Is that supported by the first derivative? From 0 to 2, is that supported by the sign of the first derivative? From 2 to 0, yes, it is supported. From 2 decreases to 0, supported. 0 to negative infinity, yes. So it appears that all the information we have from the first derivative and from the function, they work well together.